pleasure to present the next speaker, Pusey from the Institute, to talk about is QBism complete?
Okay, so I'd like to start by thanking the organisers for inviting me to this conference. It's been very fun so far, and to sort of apologise for abusing that invitation to kind of give a very vague talk that I could never have got accepted as a contributed talk to a conference. Yeah, it's kind of a type of talk I've never really tried to give before. I'm just going to mostly be talking about other people's work rather than anything I've done. Okay, so the idea is to talk about the information-theoretic, loosely speaking, interpretation you've just heard about, QBism. And I'm going to be focused mostly on sort of what QBism is saying about the world, broadly speaking. My plan for this talk has sort of evolved quite considerably as I've been preparing it. The thing that got me started was I saw a talk by David Mermin at the 50 Years of Bell's Theorem conference. And when I saw that talk, I was like, okay, finally I understand QBism and I understand why I don't like it. And so I can just go to this conference and I can just do a hatchet job on QBism and nobody will ever work on it ever again. But then I thought, well, if I'm going to give a talk about something, I should probably read some more of the papers. And I realized that there are kind of some nuances that maybe I hadn't got from David Mermin's talk. And so that's when I came up with the title you see in the abstract, which kind of talks about these two different possibilities of QBism being 80% complete or 20% complete, with the sort of 80% being what I took away from David Mermin's talk and the 20% this kind of different view I felt I got from reading the papers. So then I'd sent that title in abstract, and then I even read some more papers, and I realized actually there's a third possibility that I hadn't considered that's actually maybe closer to what people like Chris Fuchs are after. And so if you were hoping to get sort of two different versions of QBism based on reading the abstract, you're going to get 3 for the price of 2, because I actually have a new title, which is 3 Cubist worlds. This is kind of a bit of a grand claim, so maybe I should give a slightly more Weasley title, which is that I'm going to talk about 3 types of world, so I'm not actually going to explain the entire world to you in this talk, in which quantum theory should be viewed as QBism suggests. Okay, but I'm just going to start by focusing on the second part and just talking a little bit about the view of quantum theory that QBism suggests. So I kind of just want to start by telling you a little bit about where I come from. This is sort of a play on an article by Fuchs and Perrier that said quantum theory doesn't need an interpretation. And I would completely disagree with that article. I think we really do need a better understanding of quantum theory. I think if you want a good argument for why we need that, they shouldn't have both come up at once, but never mind. You can't do any better than this article by Bell, whose title has somehow been obscured here. It's called Against Measurement from 1990. And he just gives a really, there's no kind of fancy philosophizing or anything. It's just like a really hard-headed physicist's account of why we just shouldn't be happy with quantum mechanics in the way it's presented in a lot of textbooks. So I think if you read that, you'll get the strongest argument I've seen for why we need a better understanding of quantum theory. But it's maybe a little bit out of date in one respect, in that although Bell grants that a lot of the foundational questions turn out not to be relevant for all practical purposes, he maybe understates just how well we can do for all practical purposes. And a lot of that is kind of thanks to the development of decoherence. And so there's this very nice article by David Wallace that really explains what decoherence has done towards kind of solving foundational questions in quantum mechanics, and like why there is still something to be solved and what exactly that is. And basically, what he shows is that what it comes down to is in the kind of conventional application of quantum theory, even with the help of decoherence, you end up having two kind of contradictory views of the quantum state in mind. When you're applying it to, loosely speaking, microscopic systems, there's normally some kind of realist interpretation of the quantum state. But then when you apply it to macroscopic systems, there's some kind of more epistemic view of quantum states. And then, once you have this kind of view that the measurement problem is being schizophrenic about the interpretation of the quantum state, the natural approach is just to pick one of those two options, okay? And he argues in this paper that you should pick the view that the quantum state is real. But the arguments aren't all that strong, in my view. In particular, he puts a lot of weight on interference phenomenon. So there's a third paper that you should read that doesn't exist yet, that's currently being written by Matt Leifer and Rob Speckens, that's going to completely dissolve the idea that interference phenomena really support the idea of a realistic interpretation of the quantum state. So once you've read all three of these papers, you're going to be completely convinced that quantum mechanics needs an interpretation, that interpretation is going to involve deciding whether the quantum state is real or whether it's epistemic, and that it's epistemic. Okay, so if that's your starting point, then it's very natural to kind of look around and see, well, has anyone sorted this out already? And I think the kind of most clearly worked out and sort of coherently presented epistemic view of quantum theory where the quantum state is epistemic is the one provided by QBism. And so that's why I think it's worth thinking about. Okay, so I want to make an important distinction that I think sort of failing to make this distinction causes a lot of misunderstanding in discussions about QBism. And that's just between the world according to QBism and quantum theory according to QBism. Because according to QBism, the topic of quantum theory is not directly the world. And so if you look at what QBism says about quantum theory and think that it's saying that about the world, then you can kind of get yourself into a bit of a mess. And so the main topic of this talk is what the world is according to QBism, but as I said, I'm going to start just by talking about quantum theory according to QBism. So you've already heard a lot of this in the last talk, so I'm not going to kind of go over the whole thing. But I think it's interesting to look at three different items in the theory, quantum theory, and what QBism says about them. So the first one is the quantum state, rho. So as we've heard, this represents, in QBism, an agent's belief about their future experiences, say. And another thing we heard a lot about was that K here just means the outcome of a measurement, or what you would normally call the outcome of a measurement. And that, again, is something that only applies to the particular agent who has elicited this measurement outcome from the world. And then finally, something that I'm not sure we heard that much about, but that's forcefully argued for in the QBism papers, is that if we're going to have a kind of subjective interpretation of the quantum state, then apparently we have to also have a subjective interpretation of the rule we use or the mathematical object we use for updating the quantum state, for example, the Hamiltonian. Okay, so let me just, and we've also already heard that there's these things called lambdas and they don't exist. So let me just say a little bit about all four of those things. So as I've kind of already told you, I do agree that the quantum state is epistemic in some way, or I think that's at least a very plausible hypothesis. And I think QBism has really managed to hone in on some of the most persuasive arguments for that position. And one of those is just that there's a representation of quantum states where they simply are probability distributions. Okay? I find this argument extremely compelling, and I've never managed to convince anybody with it. So I don't quite understand what's going on there. But to me, if something just is a probability distribution, then you should probably interpret it the same way as you interpret any other probability distribution. And I think Bayesianism is a very good way of interpreting probability distributions, and therefore it's very likely that quantum states should be interpreted along the same lines. And then the other argument is using Einstein's arguments and maybe just kind of pulling back a bit from some of the implicit assumptions that he was making, but realizing that you can still extract an argument that if the quantum state is real in some kind of simplistic sense, then there's a way in which actions taken remotely can influence that thing. This is deeply problematic, and so it seems like if the quantum state is going to be real, it shouldn't be real in any simple way. And I'm putting these weasel words in about simple because I think probably the many worlds interpretation evades this argument because when I sit here making measurements on one half of an entangled state and updating the state for the other half, really the entire situation is just one big wave function, and those different states that I'm talking about are just kind of relative to the branch that I've ended up in, and so the argument doesn't quite go through. But I think this argument is a very persuasive argument against kind of the very naive kind of realism about quantum states that you might find in a lot of textbooks. Okay, so I'm sort of 90% on board with this first one. And then these lambdas, this idea that should we be looking for variables that allow us to predict measurement outcomes better than quantum mechanics? So I think here I'm kind of coming from quite a different place. So I would completely disagree with something Rudinger said in response to a question about should we take the same attitude to Newtonian mechanics and all these other theories? Are these all theories about how agents should structure their beliefs, yada, yada, yada? For me, the answer to that is no, okay? All the physical theories we had before quantum mechanics, I think, can be given a completely unproblematic realist reading. And that reading is the best explanation for why those theories are so useful, and so we should adopt it. And then if you take that point of view, then, like, as I think it's pretty clear Einstein did, it's very natural to try and look for a very similar way of talking about quantum theory. So, my starting point would not be that it's a bad idea to look for these kind of variables, but we know a lot more than Einstein did. We have all these Nogo theorems that are just sort of piling problem upon problem if you try and do this. And I think it's maybe now got to the point where this idea, at least in the kind of most straightforward way as captured by the ontological models framework, could be abandoned. So although I'm kind of starting from a very, or maybe starting from a very different place, I think I broadly agree with the conclusion in the particular case of quantum theory. Okay, And then the next thing we heard was that the outcome of the measurement is not like it was in the Copenhagen interpretation, say, some objective mark on a paper, but it was some feature of an agent's experience that's private to that agent. And for a long time, I found this a little bit puzzling. This is often used in QBism papers to evade no-go arguments, for example. But actually, as soon as you reject the existence of variables that allow you to predict the results of measurements better than quantum mechanics does, you've basically already undercut all of the standard no-go results. And so it was very unclear to me why they were taking this extra step of, given that they already had subjectivity for the quantum state, they'd already rejected any kind of simplistic completion of quantum mechanics, why were they also rejecting just the objective existence of measurement outcomes, which doesn't seem that problematic? And really the only argument for it is sort of Wigner's friends type experiments, where Wigner's friend has done a measurement, but Wigner is outside the laboratory, and he describes his friend as being in a superposition of experiencing two different measurement outcomes. But once you've read this paper, forthcoming paper on interference, you'll see that being in a superposition of, and you can see this already, this paper is based on Rob Specken's toy model, and you can see this already in the toy model. Being in a superposition of two different things does not straightforwardly imply that neither of those things is true. So a superposition of spin up and spin down is certainly something different from a mixture of spin up and spin down, but that doesn't mean that it's false that the spin is up or down. And so for Wigner to say that his friend is in a superposition of experiencing or for Wigner to apply a state that has a superposition of two different experiences for his friend doesn't actually mean on its own that his friend can't have, or that Wigner even himself can't think of his friend as having experienced an outcome. So I always found those arguments a little bit flaky. And I think but the response to that should be, well, if Wigner applies this superposition but also believes that the friend experienced an outcome, isn't this just hidden variables again? And it kind of is, but it seems like it's a more harmless type because we're only talking about, say, one basis, whereas all the no-go theorems, you have to kind of combine the results from different bases. So you might have thought that like the objectivity of measurement outcomes, although superficially it looks like it's going to be vulnerable to no-go type arguments, you might think that it would somehow escape them and that you could retain it. But there's been a paper very recently that I think is very interesting that gives a type of no-go result which doesn't talk about these lambdas that are allowing you to predict results of measurements better than quantum mechanics. The only thing this no-go result talks about are the actual results of actual measurements that have been experienced by actual people, which I think is very interesting. So I want to actually try and explain that result to you. And I'm not going to present exactly the argument given in the paper. I'm going to present a different version that I got from Louis Massanes via a comment by Jonathan Oppenheim on psi-rate. So this is a very modern way to hear an argument. And I think it gets across all the essential features, but is much easier to understand. OK, so what's the argument? So we're going to start with just a regular Bell experiment. OK? So over here, I'm preparing some kind of entangled state. Here I have Alice choosing between two different measurements, measurement 1 or measurement 2. I have Bob choosing between two different measurements, 1 and 2. They're getting binary outcomes, say 1 or 2. And it turns out that the statistics of those outcomes violate the CHSH inequality. Okay, so so far so boring, and apparently no problem for anyone who rejects this idea that we need to explain where those outcomes came from. All right, so the next step in the argument is just to say, well, let's just focus on the version of the experiment where Alice does her first measurement and Bob does his first measurement. And then it turns out that Alice and Bob are a little bit lazy, so they're going to subcontract the doing of this measurement to their friends. Okay? So the measurement A1 is now being performed by Alice's friend, and the measurement B1 is now being performed by Bob's friend. Okay. So now Alice is sort of sitting in the comfort of her armchair whilst her friend is busy doing this experiment. She's said to the friend, I'm not interested in the outcome of the measurement. You just go away and do it. So from the point of view of Alice, everything that's going on in her friend's laboratory is just some great big unitary. Okay? So this is sort of the same sort of argument you hear in Wigner's friend. So now I'm going to think of A1 as just being a great big unitary that takes this half of the entangled state and couples it to a huge number of degrees of freedom in Alice's friend's laboratory, okay? Including her brain and her lab book and all this other stuff. Okay, but since that is a unitary, Alice can come along later and just apply the inverse of that unitary, okay? And likewise, Bob is going to come along and apply the inverse of the unitary that describes what his friend did. Well, so now we've just got a unitary and its inverse, so nothing's happened, and likewise here. And then the final step is that Alice herself does what was her second measurement in the original Bell scenario, and Bob does what was his second measurement in the original Bell scenario. Okay, so now let's make the assumption that both Alice, Bob, Alice's friend, and Bob's friend all experienced objective measurement outcomes that it's legitimate for us to talk about. In particular, what that means is that there's a joint probability distribution for what Alice gets, what Bob gets, what Alice's friend gets, and what Bob's friend gets. Okay? Because Alice, certainly experienced some outcome, and we're just assuming for the sake of argument that that experience was an objective phenomenon that it's okay to talk about, even though we're not Alice's friend. Okay, so these four variables exist, and there's going to be some joint probability distribution for them. Once we have that joint probability distribution, we can clearly calculate these marginals. And these marginals are something we can plug into the CHSH inequality, and we're going to find that the inequality is satisfied for the simple reason that they all came from a single joint probability distribution. Okay? So it's mathematically equivalent to Bell's local causality condition to just assume a joint distribution over all the possible outcomes. But these are no longer counterfactual possibilities. Okay? These are all measurements that were actually done and whose result was actually experienced by some actual person. Okay? All right, but now we apply a bit of quantum mechanics. And we try and calculate, say, this joint probability distribution using quantum mechanics. Well, it seems pretty simple, right? It's just Alice doing her measurement, Alice's friend doing her measurement A1, Bob's friend doing his measurement B1 on the entangled state rho. So why would that be any different than it was in the original Bell scenario? This one here is maybe a little bit stickier, but surely Alice's friend can apply quantum mechanics to predict what Bob's measurement result is going to be. Okay, so Alice is sitting in her lab. She does her measurement on her half of the entangled state. She gets a result. She uses that to update the state over here. Then she applies this unitary to it. She applies the inverse of this unitary, so that does nothing. And then from that, she can make a prediction about Bob's result. And that's, again, since this is just the identity, going to be exactly the same prediction as you would have got in the original Bell scenario, where Alice had just immediately done measurement 1 and Bob had immediately done measurement 2. Okay? You can make a symmetrical argument to say that this is going to be the same as it would have been in the Bell scenario. This time it's Bob's friend applying quantum mechanics. And finally, this is probably the least controversial one. At the end of the experiment, these measurement results still exist, so we can actually look at them, and we can see that this is just the entangled state with a big identity, followed by Alice's second measurement and Bob's second measurement. So this is, again, going to be exactly what it was in the Bell scenario. But I told you when I set up the Bell scenario that it violated the CHSH inequality, and so we have a contradiction. If you've read the paper, then this might look a little bit different. There's really two differences. One is that instead of just using any old violation of the CHSH inequality, they use the Hardy paradox. And so the contradiction has a kind of more logical flavor rather than just being that the probabilities violate an inequality. So you might prefer that, but I'm not sure it's really a fundamental difference. And the other difference is that instead of having Alice's friend measure half of an entangled state, what she does is just uses a quantum random number generator to generate her outcome, and then prepares what would have been the collapsed state for Bob and sends it to him. And quantum mechanically, this is just totally equivalent. And I think the idea here is to somehow push your intuitions in a way that says that, well, yeah, it's a bit weird if Alice does some measurement on an entangled state and then this weird inverse unitary happens. Like, I'm not sure what to say about that. But surely if Alice just, has a homemade quantum state that she's prepared herself and then sent to Bob, like, we can't question that that's just going to behave the way it normally does. But I'm not convinced that this is like really a difference. I think Alice's measurement result counts just as much as a preparation of Bob's system in this scenario as it would be if she directly prepared a system and sent it to Bob. So for me, this version of the argument really captures everything that's going on in the paper. All right, so again, this is a situation where my kind of prejudice is pointed in one direction, but there seems to be a Nogo theorem pointing in a different direction. And I think, I don't want to sort of take a firm position on exactly how this Nogo theorem should be dealt with, but I do think it shows that, at least in some sense, whatever kind of maneuver you do to, if indeed you do want to do a maneuver to avoid non-locality in the Bell scenario, you're going to have to apply some kind of similar maneuver to the actual results of measurements in this scenario. So, whatever game you're playing, it can't just be restricted to the microscopic level. It really has to affect actual measurement outcomes as well, which I think is quite surprising because none of the previous Nogo theorems suggested that. Okay, so again, I'm sort of reluctantly, at least, willing to entertain this possibility that measurement outcomes aren't objective, at least in any straightforward way. The third one was Hamiltonians. here, maybe this history is just going to repeat itself and someone's going to come up with a Nogo theorem that shows that these have to be subjective. But so far I haven't seen one. And the arguments in the QBism papers I don't find persuasive because it seems they would apply just as much in Rob's toy theory. And in the toy theory, the dynamics is objective by construction. So I think I've yet to see a convincing argument that you really have to go this far. And it's also, this isn't really a good argument, but it's a little bit troubling if Hamiltonians are subjective, because some of them are extremely expensive. So I'm not going to explain every part of this in detail, but here's the rest of it. This has taken particle physicists, this is the Lagrangian of the standard model, and it's taken physicists a long time to discover it, and it's cost taxpayers a lot of money. And it's, to put it mildly, it's a little bit odd if all that was happening in that process was that the particle physicists were sort of in some collective that's trying to come up with a better way to gamble on future particle physics experiments. I'm not sure how willing taxpayers would have been to fund such a thing. I think the taxpayers were told that these experiments were actually finding out something about the world. So, maybe they have all been hoodwinked. As I said, this isn't really a good argument, but I think we at least need to be clear about what we're saying if we say that Hamiltonians are subjective. So that's kind of the one I would say at this point, least convinced by. All right, but how am I doing for time?
There are 28. I count 38 minutes left and then we're tired. So, 5 minutes.
Okay. Great. So.
5 minutes or so.
Okay, so 5 minutes for the main topic of my talk. As I've said, QBism makes very specific claims about how we should interpret quantum theory. I buy some of them, others I'm less sure about. But broadly speaking, quantum theory is some kind of theory about how agents should structure their beliefs about future experiences, say. Okay. So now let me, for the rest of the talk, just take this position for granted. Okay? So this is what quantum theory is all about. Where does this leave us? Does this sort of mean, if you've read Bell's article, you'll see there's a rant in there about how science is about so much more than the results of piddling laboratory experiments. Maybe to this he would say science is about so much more than piddling experiences. I don't know. Okay, so what does this, just granting that this is the correct view of quantum theory, what can we say about the world? And I'm going to give you 3 different possibilities. The first is just that, well, all we can say about the world is that quantum theory is the best way for agents to structure their beliefs about future experiences. Okay? And this is the sort of version where QBism is 80% complete, because all they have to do is maybe come up with a slightly better derivation of the Born rule from some nice principles or whatever, maybe prove the existence of SIC-POVMs in every dimension, just small problems like that. But once you've done that, once you've totally satisfied yourself about quantum theory, maybe there's just not much else you can say. And I think in most of the criticisms I've heard of QBism, particularly the kind of informal sort of complaints that you'll hear sort of in the pub when people are talking about QBism, they really seem to be just taking for granted that this is the most we're ever going to get from QBism. And one of the complaints you'll hear is that this is solipsistic. And I think that's just wrong. So this would be a solipsistic world. It's a single agent who just has experiences. Okay? There's nothing that causes those experiences. There's no world that those experiences come from. It's just this agent. But that's, even in this minimal world, that's not what QBism is saying. Okay? It's saying there is a world out there, but all we can say about it, at least at the quantum level, is that the best way for an agent to structure their beliefs about future experiences that that world's going to induce are using quantum theory. So I don't think that's the right criticism. But there is something problematic, I would say, about this world, which is that apparently the only statement we can make about it is one that involves agents. Okay? So quantum theory was this theory for agents, and apparently all we can say about the world is that this is the right theory for agents to use, which is a little bit problematic if you think that agents are ordinary physical systems made out of ordinary matter. And this is apparently a very thorny problem in the philosophy of mind. So I'm just going to give you a brief tour of the philosophy of mind. There's this thing called physicalism, which is what I just said. That's correct. And then all of this stuff is wrong. OK, so this is why you shouldn't believe, or at least you shouldn't be satisfied with this minimal cubist world. It's not because it's solipsistic. It's just because you can't really square it with the idea that agents are physical systems just like anything else, because then how on earth did it end up, the term agent end up being there in this only statement we can make about the world? Do the founders of QBism want this minimal world that I've described? I don't think so. When I went back and read the papers, I found statements like this, or like this. And I think it seems to me that these are pretty clear statements that are urging us to look for more than just this minimal view of the world. Quantum theory is just the start of our adventure. The quantum world is still ahead of us. But maybe I didn't just completely misunderstand Mermin's talk. Maybe he would be quite happy with this minimal world, because in his paper he says science is about the interface between the experience of any particular person and the subset of the world that is external to that particular user. So if you think this is what science is about, then maybe you'd be happy with this minimal world. A second possibility is that the quantum world is made of, there's a homework problem here, and it's behaving according to some laws. And then a corollary of those statements is that in the particular case that stuff has been arranged into an agent, the best way for that agent to structure his beliefs about future experiences is to use quantum theory. All right. And then we've got no dubious philosophy of mind going on. Agents are just certain arrangements of stuff. And when stuff is arranged in that way, it's a good idea for that stuff to use quantum theory. So I thought, great, this is what they're looking for. And this was the 20% complete version. And then I read a bit more, and I found Fuchs explicitly says you have to throw away the idea that everything is made of essence X before even starting. So I thought, oh, OK, maybe I've got the wrong end of the stick. And apparently, in thinking that agency is a derivable concept, I'm a vicious abstractionist. Apparently, what we should be looking for is something called that I'm calling here a Jamesian quantum world, which I don't really know much about. Apparently, you have to read a lot of long books, and you'll find that the world is kind of much richer and more complicated than sort of my simple way of looking at things could ever do justice to. And that's the kind of world we should be looking for. And then again, quantum theory will turn out to be the right theory for agents in that world. All right, so to summarize, I've outlined 3 possible ways in which cubism could be the right way to talk about quantum theory. None of them are solipsist. The minimal one, where we said all we can say about the world is that quantum theory is the best theory for agents, seems to require some kind of primitive notion of agents. I don't see any reason why we can't get rid of that, but apparently there are good reasons. Sort of very hesitantly putting Mermin as a proponent of this view. I would be, it would be great if he was here, or if somebody who knows him better than me can comment on that. Maybe I could put myself as a proponent of this mundane world, at least on weekends. And I think it's pretty clear that Fuchs is advocating for this. And finally, in the minimal world, once we've understood quantum theory, there's not really much more to say. But in both my kind of mundane world and Fuchs's Jamesian world, I think even once we've understood what quantum theory means, there's still lots more to say. So thank you very much.
Richard?
Thanks for a lovely talk. I particularly enjoyed your simplified version of the end paper that you referred to, revolving the simplified version, which I've been struggling with. I can understand what you said. So thank you very much for that. I'm still going to have to think hard about it because I don't like the conclusion, though I do like the premises. But that's my problem. Okay? Let's see, what else to say? I think that you nailed a lot of what I understand about cubism. And it's been very useful. And I'd like to get a copy of your talk and check up on some of the reference. Thank you.
Okay, thanks.
Yeah, I like what you're doing here. In the 60s, I.J. Good wrote a letter to the Journal of the American Statistical Society, which was titled 46,656 Varieties of Bayesianism. It was meant to do away with this practice of talking as if Bayesianism were a single view. It didn't work. But I think we should similarly stop thinking of cubism as a single view. I think one thing that's clear is that there are actually, at the time there were 46,656 Bayesians. There were more varieties of Bayesian than there were Bayesians. I think it's clear to me that there are actually more varieties of cubism than there are cubists. And I mean, this is going back to Lucian's comment either. I really, even though he doesn't really advertise it, I think that what Chris Fuchs has wanted Bayesianism to be, and cubism to be, and what it's going to do, it really needs to be timed in this. The sorts of things he's saying now is very different from what he was saying 10 or 15 years ago. So it'd be nice. So it's a nice task to sort of do a classification of different varieties of cubism.
So on the subject of what the Hamiltonian is objective or subjective, I think by Matt Leeper some years ago persuaded me that to be consistent with other commitments of cubism, you really do have to take Hamiltonian as subjective. So the reason you can get away with not taking them to be subjective in the toy theory is that although quantum states in the toy theory, or the analog of quantum states in the toy theory, are states of knowledge, they do make probability 0 and 1 assignments to certain kinds of properties. Like the analog of an entangled state will say that, for example, the state of two systems are definitely the same. And in those contexts, you say, and those probability 1 assignments mean that I can trust that to be an objective fact about the world. So the status of the Hamiltonian gets linked to your interpretation of quantum states via the Troy-General-Kasky isomorphism. So I remember Chris Fuchs tried to persuade me that I should take unitaries to be epistemic on the grounds that there's this isomorphism between states and unitaries. And the toy theory told me, well, no, because not everything about a quantum state is epistemic. There's some things that I can say are definitely objective, and therefore like an identity transformation is something objective in the toy theory, just like the relation between two systems can be objective. But if you're committed to the view that probability 0 and 1 are not warranting claims about objective truth, but also merely subjective claims that says I would stake my life on this bet, but they have no more claim to describing reality, then I think the Troy-General-Kasky isomorphism forces you to say the same thing about the unitaries as well. That there's no the toy theory doesn't provide any reason for saying that the unitaries are any more objective than entangled states are. So to my mind, a consistent cubist view, if you're going to be subjective about probability 1 assignments, then you're going to have to take unitaries to be subjective as well.
So I think you've convinced me that if you don't say there's anything objective about probability 0s and 1, then the argument with the toy theory maybe falls apart. But I would still want like an actual argument that convinces me that I should view them as subjective. Right? I was just taking the toy theory to be a counter example to the arguments that I'd seen. So are you saying that some of those arguments actually are?
I think the argument that's being supplied, and I don't know if you think it's a good one or not, is just the existence of the Troy-General-Kasky isomorphism. It's an isomorphism between things that I've acknowledged are completely subjective at the level of two systems. How could it be describing something non-subjective at the level of two systems that are separated in time? So
I see.
I agree that's not a particularly strong argument maybe, but that's, I think, the positive argument in favor of treating them subjectively.
And the completely subjective means including the 1s and 0s.
Yes, exactly. That's what I mean.
Yeah, I could maybe buy that. So are you worried about what the people at the LHC are doing?
Well, I think I would not quite put myself in the category of, I thought, well, maybe I'm a mundane cubist, but I think I still disagree about the claim that probability 0 and 1 assignments are also subjective. I think you can get objectivity out of those sorts of assignments. So I would agree with your assessment of the LHC, and I would locate my disagreement with cubism there, the interpretation of probability 0 and 1.
Pusey? So slightly off topic, the experiment you explained was it Renner and then the version you gave. So my first thought was it's just an outright paradox, and then I thought we wanted to put it in the Boyd-Bone model. Understand right? Have you done that? Do you know how it?
Done is a strong word. I've hand-waved about it. So I think what would happen in the de Broglie-Bohm theory is that Alice's friend's prediction of Bob's measurement outcome would just turn out to be wrong. So her application of quantum theory would actually not be supported by the de Broglie-Bohm theory. Because of
non-local effects of the
because of the non-local effects of these guys. Yeah. So it's a little bit, it's a little bit kind of surprising given that people normally say that that Bohm's theory is kind of empirically equivalent to quantum theory. It looks like this is a situation where, like, Alice's prediction using quantum theory turns out not to be true, but luckily her memory's been erased. So
it's still saved by memory erasure.
Right. But of course, I really don't like that resolution because then, that's just using action at a distance to get out of the
It's
argument.
a matter of calculation in this Boyd-Bone model. You're just doing calculations of outcomes.
Yeah,
So, and it sounds like that's the right resolution.
Yeah, I think this is probably the right resolution because this is actually very similar to there was a debate between Reinhard Werner and the Bohmians where he basically set up a Hamiltonian that more or less does this evolution. Like, he wasn't actually talking about putting a person there, but I think it would amount to the same thing.
Can I just, on this part, can I just ask a question on how the argument works? Because I haven't read the paper and you have to agree with it. So Alice gets a result, and you say that she updates her state and makes predictions about, on the basis of that result, and make predictions about what happens at Bob's end on the basis of that. But that's what not. So she's collapsing the state basically.
Yeah.
The Bohmian will say don't do that. The Bohm says the state does not collapse. She gets a result, but both terms of the state are still there.
Yeah, but normally they would say there's this thing. What's it called?
There's effective collapse.
Effective collapse.
But it's not real collapse. It's only effective collapse, and effective. It's effective because in practice it's hard to undo.
Right.
Now Now what you've done is put in unitaries the by hypothesis undo effective collapse. That's what a Bowman would say about that.
Yeah, I think that's a better way.
Right. Yeah. So so it's not actually inconsistent.
Is it
Yeah.
So, in the original version of the paper,
Yeah.
so I'm in contact with relatives who wrote the paper, I'm in contact with the Bowmans, who now agree that you cannot apply Bowman mechanics to the experience of individual users, but only globally. And they do agree as well that it would give different predictions from quantum theory, but in very unlikely situations, like this one here. There are things that in the original paper you don't do the measurements.
Right.
So you just, it's like Alice in the future makes predictions about what her friend in the past would have guessed that Bob in the future would have guessed.
Okay, and
gets
that,
a contradiction.
okay, we can talk about it later, because when I first saw this, it seemed to me virtually identical to the argument that a bunch of Bohmians used for the conclusion that in a relativistic context, the distribution postulate can't be satisfied along arbitrary foliation. So you can say, we'll get the right correlation between A1 and B1, we'll get the right correlation with A2 and B2, but we can't get the right correlation between A1 and B2.
So you're saying that this version is missing something that's present in the other version?
I don't want to say this. But I'm also not saying.
Okay, Jake?
Thanks. Sorry, this is a very sort of general naive question, but it's about relationship. What the quantum Bayesianist QBist says about relationship between quantum theory and other physical theories. So, in particular, if I take a low energy limit of the state of quantum field that's particular states of the quantum field, their classical limit is just a mode of a classical field. But you said that you wanted to interpret all the other theories realistically. So you think that the mode of the classical electromagnetic field is this real physical thing, this wave, electromagnetic wave, and yet the quantum field theoretic state that has that as its limit is this epistemic thing. It's just about what we should expect. So just sort of wondering what you guys have to say about how by taking a limit I can turn something epistemic into something altered.
Yeah, I think that's a very good question, and I think there's probably lots of interesting research problems in answering that question. Very loosely, I would say that it could easily be the case that despite the classical electromagnetic wave, say, being objective, there are still some things you don't know when you know that wave. And so it could be that the epistemic part of the quantum state is reflecting that uncertainty rather than, in that limit, there's no uncertainty about the classical electromagnetic wave, say. There's rather uncertainty about some other degrees of freedom. So I don't think it's impossible to square that circle, but I think it will be difficult for sure. And a resolution like that could plausibly depend on this issue of how you interpret 0-1 probabilities, for example.
Well, it was a comment on the discussions on trying to go with Rob. So you're talking about this argument from the Troy Yamakowski isomorphism. I just mainly want to say I don't stand by that argument anymore. The reason being, like, in light of the recent stuff, the thing that's isomorphic to dynamics is the conditional state. So the thing that's isomorphic to the quantum state is the temporal Drake state. And that involves the initial state as well. And so it's when you combine those two things together, you should reason that thing is subjective. But that could be entirely due to the fact that the initial state is subjective. I also wanted to say one more thing about what I said in that paper, which is like relevant to whether the standard model Hamiltonians is agreeing or not. So the position I took there is like, well, so what? So long as the symmetries that thing reflects are real, you still have like sort of 90% of what you need. You've got to decide basically which representations of those symmetries you're going to use, and then that's pretty much going to force what Hamiltonian is.
What about the parameters?
Well, there's three parameters, of course, yeah, but most of those are determined experimentally anyway. But most of those are determined from experimental data as it is, but the sort of real content of the standard model seems to be like these symmetries.
I think that would be better, but I think the people at the LHC would still be a bit disappointed if they found out that like the mass of the Higgs was subjective. So, but yeah, if the symmetries are objective, that's a good start.
Just as a remark on what you said about the many versions of cubism. I think actually that Chris Fuchs in his writings is remarkably consistent. So of course there's some developments. But I mean, if you know him, if you know his writing, the way he always refers back to his own earlier things and quotes himself extensively, for instance. I think it's unfair to say that there's a big variability. It has been remarkably consistent, despite some clarifications and developments. But obviously, it's. I mean, of course, there's different ways to move it and develop.
Yeah, I think I'd broadly agree with that. I think there was. I mean, I think Chris himself in his writing said that there was a big shift from this kind of knowledge version to this belief version at some point.
But that was never called QBism.
Okay, fine. Yes, there's a difference between positions Chris Fuchs has espoused and cubism, for sure. And yeah, what about the Jamesian stuff? Has that been there since the label cubism has been there?
Yes.
Okay, fair enough. That doesn't mean there aren't other varieties of cubism, it just means they haven't been put forward. So, yeah.
Related to James' question, partly answered your question. So early on in the talk, you said that you thought it was natural to be a realist about classical mechanics.
Can you speak up, please?
So early on in the talk, you said it was natural to be a realist about classical mechanics. And I think the answer that came out of so I was going to ask the question about why that's natural. I think the answer was that it's probability 1. So if that's not the answer, then what do you find natural about being a realist vis-a-vis classical mechanics that isn't present in
that there are mathematical objects in the theory that you can kind of ascribe to, you can grant an objective existence, and that seems totally unproblematic.
What do you mean by objective existence? So I guess that's what
Like if the world truly was described by Newtonian mechanics, I don't think there would be any paradoxes or Nogo theorems or anything in saying that a particle really does have a position and a momentum at all times. Like, I think the theory is totally comfortable with that in a way that quantum theory isn't.
Just if I may intervene on the probability 0 and 1. I mean, a number of people here are following of definity. And in definitive theory, probability 0 and 1 are subjective. They're very different from certainty. So he talks first in the logic of certainty. And only after you talk about the logic of certainty, you have the uncertainty. The probability of 0 and 1 are different from certainty. That means that it's the highest degree of belief that you have, but it's not certainty. It's different. And in certain situations in which you have, like, for instance, continuity, you can have a probability 0 that is not false, and you can have probability 1 that is not truth. Could be measure 1, and still, so there is a big difference, at least for definite.
Would you say that it extends also to finite sample spaces?
It is in general. It is a view that what is the realm of probability, the logic of uncertainty, which is probability, everything is subjective.
Well, I agree with that. Only the argument that the continuous sample somehow seems to hide this in a technicality. So
yeah, it's just an example, but I mean the philosophical view is that what is certain is not part of probability. It's the logic that actually bound the events that you can have probability for. So it's, and yeah, there is, I mean, there are people like Isaac Levi or other people who agree with that. That probability 1 and 0 are not true or falsity. So there is, so those who follow, just to cut it short, I mean, those who follow definitely have motivation, internal motivation, to take probability 1 and 0 as subjective, not objective.
Is there anyone else? Because I said.
Yeah, there's a question about.
Okay.
Sorry.
I'm hoping you can clarify something you said in there for me. You said that QBism is about using quantum mechanics to update each agent's own subjective belief about the world, unless those probabilities of belief, which may turn out to be wrong. But there is still some underlying ontological world that they just all have imperfect knowledge of. Was that what you said, roughly?
I was, like, there is some external world, yeah. But, like, I was willing to get on board with the idea that there's nothing about that world that determines measurement outcomes.
Okay. And then my other question is, in that world, are there non-local influences in order to be consistent with two agents' experiences or something like that?
No. I mean, I think if there really are non-local influences in the world, then we could probably just adopt a scientific position and be done with it. Like, I think one of the main attractions of going down this road is to avoid that kind of thing.
Yeah, so you made this was sort of a joke about Hamiltonians being very expensive, but can't the same sort of line of reasoning apply to quantum states too? Aren't quantum states very expensive? One way to think about what the LHC is doing is spending a lot of money to prepare certain kinds of quantum states and see what happens. And what I mean, actually, there's a serious question which I've never really gotten a good answer from QBism from. So suppose someone tells me, look, I've managed to prepare create a device that prepares photons in highly entangled states and get that entanglement to persist over a long distance. I say congratulations. That was a good thing to do, and we very rightly respect the first people to do it. Is there not a matter of fact about that claim that they actually managed to produce long distance entanglement?
Like, I think they've certainly done something, but
Like, obviously,
there might be.
they've done something that that I have not done when I just say, you know, I'm setting my degrees of belief to the ones appropriate to this entangled state. Like, that's easy to do.
No, I think
what they've done is hard to do.
I think they've. I think this is a tough question, but I think one way it could end up working out is that what they have done is taken some actions that cause the sort of prior beliefs that are widely shared by scientists to lead to a state assignment of an entangled state. Whereas your state assignment of an entangled state, you just kind of made up on the spot, right? And you would find it very difficult to convince anyone else to assign that quantum state.
But even if I were very charismatic and did convince them, they'd be wrong.
Well, no, that's the idea. They wouldn't be wrong.
Yeah, they would be wrong. Yeah.
But isn't this all? I mean, it seems clear to me that we can spin it either in that realist way and say, well, I mean, since they did something and they can repeat it clearly, it's right and it corresponds to something real. Or you could say, well, they just did something useful. Right? It's actually useful and you can use it later, and this is why it cost a lot of money. I think these are two natural ways of looking at it. I don't think anyone should.
The question is, what is the useful action they've taken?
This is good. There's a matter of fact about whether what they have done could be used for certain purposes.
But I'm not quite sure that it's a loaded phrase. It's a matter of fact.
Yes, exactly.
But I don't see why. I mean, that's clearly. I mean, there is a well-rehearsed way of talking about things that you present, but I don't see why that is necessarily the only one. Why it is true.
Like, I'm not sure this is really all that different from like in a classical kind of world where you're applying Bayesian probability theory. What does it mean for one coin to be fair and one coin to be biased? And I think what it ultimately means is that like certain natural beliefs about how that coin is going to be tossed will, when you apply the rules of probability theory, give you certain probability distributions.
I think you're right. I think that even in a classical case, there are things that play the role of the objective objective chances. You know, by the way, Pittsburgh, all you physicists out there, it's a terminological distinction, difference between philosophers who work in probability theory and physicists influenced by Chris Fuchs, because Chris uses the word Bayesian to mean denial of objective probability, whereas outside that, in the rest of the world, Bayesian means simply willing to countenance prior probabilities and test priorities as subjective probabilities. And in I.K. Hood's 46,656 varieties of Bayesianism, one of the classification is accept objective chances or use them without commitment to whether they exist or not. It's only 1/3 of those varieties actually deny objective chance. So that's just a potential confusion. You know. But yeah, I actually think that actually a talk I gave at a conference organized by Chris Fuchs was being Bayesian, I believe in objective chance, and by the way, so did Bayes.
Set the record straight. I mean, here you're right. Things have changed. The QBism is not quantum Bayesianism, and it started 2010, 6 years ago. And it is right. Until then, we used Bayesianism in this confusing way, but not since 2010.
Okay.
So this is
progress.
Yes,
progress. Yes.
Is it a comment on this?
Yes. So I just wondered whether perhaps a good QBist response to Wayne's question is the analog of the response to the question, what is a physicist doing when they're resolving their uncertainty about which quantum state holds? So there's this quantum state tomography, and there's lots of experiments with we're discovering which quantum state pertains. And the QBist response is, well, we respond to that in the same way that Diff and Eddy responded to the question, how does one learn the probability distribution that's associated with the dice. It doesn't mean that that's a property of dice. No, it means if you have an assumption of exchangeability about all future dice rolls, then when you write down what your probability assignment is, it looks like a probability assignment over different biases for your dice, but it's really an assignment about your future expectations. So it seems like that in there might be an answer to this question of, what have we done when we've updated our beliefs to say, oh, it's this entanglement with fidelity a little bit higher than we had before. It's a statement about expectations of beliefs for sequences of measurements in the future.
Yeah, I think that's a very good point. It is pretty much works pretty much in rational definite context in quantum. And so if I thought that Definiti's response worked, then I would also accept it in quantum context.
This is a very small point. Maybe I could just make it and then yeah, in the original paper by Colbeck and Rotman, which you gave a simplified version of, the title.
It's not Colbeck and Rotman.
The title was something like, "Is a self-consistent one-world interpretation of quantum theory?"
Yeah, right. Yeah.
Right. So I took it that they were arguing from some kind of Aretian view when I read that. Is that just a misconception of what they were up to? Is that what they took to be the motivation behind their argument?
I don't know what they took to be the motivation, but certainly Everett would be one easy way out of this argument. But I think saying that a measurement result is a kind of private experience of an agent rather than some kind of property out there in the world gets you out of it.
Right,
just
and it's
as well.
not clear from anything in the paper or anything you know about these guys which they would go for.
I don't know.
I just wanted to, so this is a little too late, but I just wanted to insert that Judea Pearl works in epidemiology, and his toy testbed is robotic soccer. So any idea that this is just about subjective beliefs is, the title of his book is Causality. It's a method of extracting definite physical causality out of a set or a network of unknowns or partially knowns. So this idea, this alternate definition that Fuchs is proposing is just, you should call it something else.
I've read Pearl's book and I've actually found it difficult to pin down exactly what his views are on kind of standard questions about the interpretation of probability.
Yeah, but I know him personally, and
okay.
Those two facts alone should tell you about Bayesianism. That his great application at UCLA is epidemiology, and his test bed is robotic soccer. So how can you possibly take out of those two facts the idea that this is just some completely subjective, unrealistic endeavor?
I guess I'm just not buying the line that robotic soccer is a counterexample to personalist Bayesian probability.
Okay.
But maybe that's another discussion.
Okay.
Thank you.
We run out of time. Is it very short there?
Well, I don't know. I just often find that people talk about objective chance versus Bayesianism or epistemic views, whatever. And then this one is really really clear that like the epistemic objective distinction is not the same as the subjective objective distinction. So James thinks that Bayesian probabilities are degrees of belief. They're nothing like in the world, but he still thinks they're objective, right? So you could be an objective Bayesian in the sense that you think that probabilities are just degrees of belief. And I think that's a response to what you just said, because you needn't think just because Bayesianism says probabilities are about guidance agents and about degrees of belief and so on, that means the same.
Yeah, okay.
Okay. Just to resist the temptation to answer these comments. Thanks very much.